Hi, my name is Seungjun Na. Our paper title is Clean Images Are Hard to Reblur, Exploiting the Ill-Post Inverse Task for Dynamic Scene Deblurring. This work was done with my colleagues Sang-Hyun Son, Jae-Rin Lee, and Kyung-Moo Lee. Deblurring aims to remove the motion blur in an image. But what if we want to do the inverse task? If we want to find the true motion blur from a single sharp image, will it be possible? The answer is not so easily. Predicting the true motion blur without giving any external information is another ill-posed problem. Then, let's think about reblurring an image, which is reconstructing the original blurry image from the deblurred image. Will it also be as difficult as blurring a sharp image? Surprisingly, despite the successful deblurring result, reblurring is much easier. What makes reblurring so easy? We found that the blur kernel direction is still observable on the imperfectly deblurred images. So, amplifying the witnessed blur footprint leads to reconstructing the original blur. Our goal is to remove such remaining blur information to make the images sharper. By noticing the difference between the deblurred and the sharp images, how can we better deblur images? We can do so by making our deblurred images hard to reblur. We propose to train our models with new reblurring laws in our joint optimization process. We build a reblurring model that has two different objectives. First, it performs blur reconstruction from the deblurred image that may not be perfectly sharp. At the same time, it learns to preserve the sharpness of clean images. Due to the optimization stability issues, we use pseudo-sharp images for training. We train the reblurring model with these two loss terms simultaneously. Jointly, we train the deblurring model with the standard L1 loss and the supervised reblurring loss. We use the reblurring model to amplify noticeable blur in the images. This lets us more focus on the blurriness of images. Thus, using the reblurring loss in addition to the L1 loss can better penalize blurriness. While our training scheme may look similar to adversarial training, however, they are conceptually different. Adversarial loss tries to make an image more realistic, but may not penalize real blurry images. On the other hand, reblurring loss makes an image sharper, regardless of the image realism. We validate the effect of the reblurring loss by comparing it with other perceptual losses, such as VGG loss and adversarial loss. In these examples, the thin pillars are better recovered from our supervised reblurring loss. In addition to the supervised reblurring loss, we could further build a self-supervised reblurring loss. If an image is sharp enough, the reblurring model should not be able to amplify the blur in it. If the reblurred image is blurry, we can optimize the deblurring model with a self-supervised loss. The test time adaptation with several iterations can further improve the image sharpness. Here on the last column, we show that applying test time adaptation steps can exhibit even better recovery of texture and face structure. Compared with the state-of-the-art, our method can successfully predict sharp texture of moving objects. We show that our reblurring loss not only improves the perceptual quality, but also improves the perception-distortion trade-off. The supervised loss improves both PSNR and the perceptual metrics such as LPIPS and NIQE. Then, applying self-supervised adaptation further emphasizes the perceptual quality. To summarize, we present a new observation that clean images are hard to reblur. We proposed a novel reblurring loss terms for better training of deblurring models, and show that self-supervised test time adaptation helps. Finally, we achieved an improved visual sharpness. Thank you for your attention.